Hi, my name is Elsa Thompson, the Survey of Chemistry, and this is unit video number 3, chapters 7 through 9. All right, so for the first question, just jump right in. This one's about soaps. Soaps are empathetic. Empathetic means that it has both nonpolar and polar parts. And then I had to draw a soap skeletal structure, and this is what one could look like right here. This blue part is the polar ionic part, and then this highlighted pink part is the nonpolar, which is the hydrocarbon tail. Soap is not soluble in water because of the nonpolar tail on it. So the tails point inwards towards each other with the polar heads facing out. So this would make the head. It would look something like here's the head and then there's the tail, like that. You can see that right here in something called a micelle, which you can see I highlighted the outside blue for where the heads are and the inside pink for where the hydrocarbon tails are at. Facing out in a sphere called a micelle, like that right there. The tails interact using London forces, and while the heads interact through mostly ion-dipole reactions. The heads face out because they are polar, and water is also polar, so if here is our micelle, this is the water on the outside. They face out because this is polar, because it's right here. This is polar, and this is polar, and because like attracts like, they go out to each other. So they are good at washing things away because the dirt and grease stick into the middle of the micelle, which you kind of see that darker pink color. I kind of didn't draw that very good, but yeah, there, the stain goes in the middle because they are also nonpolar, and the middle is nonpolar, and like attracts like, so it goes in the middle. The dirt and grease will stay in the middle because they trap each other in there because it's nonpolar, and then polar and polar with the water. So then they get washed down with the water because it's not soluble in the water, so it just stays in there, and then you wash it away down the drain. That was 1. 2. So right here is mainly about concentration. So the first one says what is the molarity, or the M, of a solution containing 0.95 moles of NaCl and 2.4 liters of solution. So this is my number 1. Here, I'll zoom in a little bit. /A. So this is the formula that I use to find moles. The mole, the solute over the liters of solution. So then I put my numbers in. I have 0.95 moles and 2.4 liters of solution, and then you just divide them two, and then you get molarities equal to 0.396. That's the number for the first one. And then for 2B, it says how many grams of dextrose must be added to prepare 250 milliliters of 3.0 mass over volume dextrose solution. So here is our formula that we use for this one, and I highlighted all the formulas in gray for this one, and the answers in purple. Anyways, we have grams of solute over milliliters of solution times 100%. Let's get the percent of this. So we're not really solving for this, we're solving for one of the things in here, so we have to put this on that, put everything on this side to get our final one. So we have 3% on this side because we need to get 3% dextrose solution. And then we have our grams of dextrose, which we don't have this yet. And then we have our 250 milliliters of the total solution because this is our solution and this is our solute. So solute because we have less of this and more of that, times 100. So first I divided by 100 to get rid of the 100. I get 0.03, and then I multiplied by 250 milliliters on both sides to get 7.5 dextrose. That's grams, so 7.5 grams of dextrose. For number 2/B, and then for C, over on this side, the question is, if a solution contains 2.0 millimoles per liter of Mg2 plus ion, what is the concentration of the solution in MEq over liters? So the formula that I found for this one was MEq over liters equals the charge of the ion times the millimoles over liters. So so down here, millimoles per liters equals 2 for this one because it's just what it is. And then milligrams of the charge on this one is plus 2 because it's positively charged ion by 2. So it equals 2. So then we have to plug the numbers in up here. And then that's the formula, and I put the numbers in right here, and then you get 2 times 2 equals 4, so equals 4. And then 4 MEQ over L is our answer there. So I didn't circle this one like I circled the rest of them. There we go. All right. And for number 3, here it is. Made this one extra beautiful. Okay. Anyways. Okay, A. This one is about acids and bases, using our Bronsted-Lowry definitions of them. Okay. A is write the chemical equation for the acid-base reaction between acetic acid, I hope I'm saying that right, acetic acid, which is our CH3COOH, and then it's aqueous solution plus H2O, which is water, and then, so gave us that, and then we wrote it out here. Ignore the highlighting, it's for B. So then we get H3O plus aqueous plus CH3COO minus, and that's also aqueous. This is a weak acid, so it doesn't fully break apart, and things are constantly switching, so it's an equilibrium equation, which is the little arrows right here, and it can also be written this way. I guess I just wrote it with 2 full arrows that way. Anyways, then the next question is label all the reactants and products using the following terms: acid, base, conjugate acid, and conjugate base. Our acid is our acetic acid, so I mean it's in the name. It's a weak acid, and then our base is our water. Our conjugate acid is our H3O plus, and our conjugate base is our CH3COO minus. That's that one. And then C says write the equilibrium constant expression for K for this reaction. So here is the equation that I used. It's K equals products over reactants, and the little brackets stand for molar concentration of. So then I plug everything in, and you get K. Let me circle it. K is equal to, in the bracket, CH3COO minus, and then another bracket, and the ending bracket, and then another starting bracket, H3O plus, and then an ending bracket, and then all over our acid in the bracket, which is CH3COOH, and then end bracket. Water isn't in this because it does not appear in equilibrium constant expressions because it is considered a constant because it's used so often. It's kind of just implied that it's there. So, all right. And then next, D says if an acetic acid is a weak acid, the value for K is the value of K greater than 1, less than 1, or equal to 1. Explain how you know. So, I wrote what it is, and then the K value for it is 1.75 times 10 to the negative 5th, which is this lovely number right here because you move the decimal, whatever. And then, so 1.75 times 10 to the negative 5th is less than 1 because this number is obviously less than 1. So for weak acids, the K is typically less than 1. So that's how I know that. And I found this number in our textbook. So yeah. Okay. E says that in the human body, pH varies drastically among different organs. How would a molecule of acetic acid behave differently in the stomach compared to the small intestine? In other words, which form of acetic acid, the acid or the conjugate base, would predominate in each organ? Explain how you know. Okay, so I wrote down all the information that's stated in that little paragraph that I just read. So the acetic acid pKa is 4.76. The stomach pH is roughly 2.8, and the small intestine pH is roughly 8. Obviously, it's different depending on what situation you're in. Anyways, so I wrote down here my little cheat sheet basically. When pH is less than pKa, the acid will predominate. When the pH is equal to pKa, it's equal. And when the pH is larger than the pKa, the conjugate base will predominate. So if we apply those rules to right here, the stomach has a pH of about 2. So it's right there. And then the pKa is 4.76, which is up here. I labeled them with colors. And so then we know that the pH is less than our pKa. So we look down here, then the acid will predominate in the stomach. So the acid in this one. And then for the small intestine, our pH is roughly 8, so pK is 4.76. So our pH is greater than our pKa. So if we look down here, the pH is greater than pKa. Look down here, then the conjugate base will predominate. So then this one is the conjugate base. There we go. So that is it. I've answered all the questions, and thank you.